So we are talking about two-dimensional ordinary differential equation systems that have special structure. And maybe I'll put that in scare quotes. We ended last time looking at some model of two different species competing, the rabbits versus the sheep. And by and large, that's kind of a generic model. It didn't have any special structure like we're going to talk about today. So by special structure, I'll go in some kind of sequence. I'll start with gradient systems, then we'll go to Hamiltonian systems, then we'll look at conservative systems, and then end with the pendulum example. I think it gives a good overview of systems with special structure. In general, in 2D, we're thinking of systems that we could write in this vector form. This is x dot, so how x changes with time is a function f of x. If we write this in terms of its components, scalar x and scalar y, then on the right-hand side, scalar f of x is just a function of x and y, possibly nonlinear, most likely nonlinear. And g on the right-hand side of the y dot equation is also a nonlinear function of x and y. So this vector x is x and y. But we can have systems that have special structure. And by special structure, I mean that the vector field f has a special form. So many systems encountered have special form for f. I guess let's say encountered in applications. So the first one we'll talk about is gradient systems. Gradient systems are those that have the form x dot equals the negative gradient, this is the gradient operator, of some scalar function v that's a function of x. So we've got the gradient, and then v is a scalar function of the two-dimensional position in phase space x. So what would we get from something like this? Let me show you an example of a function v and its gradient. So here's a function. This is the height, if you want, v as a function of x and y. So this is just a height function. The gradient at any point is the vector that's pointing in the direction of the deepest descent. All right, gradient of v, it's partial v, partial x, partial v, partial y. And we're showing the field of the gradient over here on the right. That's what these little vectors are showing. For this surface on the left, gradient shown at a grid of points. The almost closed curves that are shown are curves of constant v. Maybe if I point one of these out, this on the right in orange, it's a surface of constant v. So we might say it's an isocontour of v. The way gradients work, gradients are always perpendicular to the isocontours of a scalar function that they're operating on. So here, right, the gradient is pointing upward towards the hilltop. So there's a hilltop right here. And then on the other side, we have the bottom of this function v. In this case, f of x is equal to the negative gradient of a scalar function v. So what will the dynamics look like? What does the vector field look like? The vector field is going to be the opposite arrow as shown in this figure. So that means everything will be going downhill because we've defined this as the negative of the gradient, so that we could use intuition about, think of a ball on this surface. Where will the ball end up? It's following the negative gradient, so it's going to end up at the bottom. So if you have a gradient system, you can have fixed points. So fixed points are possible, but no periodic orbits. And this is because if you were to calculate how is the value of v changing along a trajectory, it's always going to be decreasing. So let's just follow the value of v along a trajectory. What would that be? So we mean v following x as a function of time. The way to calculate how this is changing with time along a trajectory is we take the derivative. So v dot, or dv dt, and now use the chain rule. We'll get gradient of v dotted with x dot. So this is gradient of v dotted with negative gradient of v along x. So this is negative the magnitude of the gradient squared. So, and we'll call this, for shorthand, call it v dot. So v dot is less than or equal to 0, and v dot equals 0 if and only if x is at a fixed point. So you can't have the closed contour, any curve, and expect that this trajectory is going to move along it. So that means there can't be periodic orbits. Everything just eventually, starting from some initial condition, it follows the negative of the gradient and it goes towards the bottom position, a local minimum. In this case, this local minimum, at least for what we've plotted, looks like a global minimum. And that's because the value of v, the height function, if you want to think of it that way, we're always going downhill until we go to the nearest local minimum. And then we can't go anywhere else. If you have a gradient system, if your system comes from the negative gradient of a scalar function, no periodic orbits are possible. There are fixed points. We haven't yet said what type of fixed points we could have. I did plot a particular type of surface here where there's just a hilltop. And so that's going to be an unstable fixed point. I think it'll be an unstable node. And then this bottom point of the well, so what it's heading towards is a stable node. So everything's coming in. But you could also have saddles. So if I plotted a saddle surface to this, you could get saddle surface. Stable and unstable fixed points, but no periodic orbits are possible if you have a gradient system. And this idea of having a scalar function of x that you take various partial derivatives of it and get the dynamics is going to be a theme as we go on through here. So this is the first type. It's not terribly interesting. It plays a role in control theory if you know about Lyapunov functions. You try to construct some v that shows that some point of interest is a minimum of your Lyapunov function. But anyway, so that's one type of special structure. Another type, the next one we'll talk about, is Hamiltonians.